Baby shawties, how are we doing? Welcome to our brand new unit. In this unit, we're going to focus on mechanical waves and we'll get into a little bit of sound. So the concept that we're going to be focusing on in this new chapter is the concept of a wave. So a wave is going to be a little bit different than what we've been talking about up to this point in the second semester here on electricity. A wave is going to have to go back to our ideas of energy. Okay, a wave is what happens. It's one way in which we transfer energy from one object to another, and it occurs when we create some sort of disturbance. Okay, and you might have seen waves in many different forms. When you hear of a wave, you might think of, like, for example, a water wave as shown here. You might think of, like, let's say in a stadium, if you go to a sporting event in a stadium where they do the wave, kind of follows that way. It's energy flowing through the crowd. You could have sound waves, light waves, but what waves are is it is energy created by some sort of disturbance that moves through a medium, and we'll talk about what a medium is, from one point to another. So to kind of give you a visual of what a wave is, imagine here this is just a wave generator. So first of all, it's a movement created by a disturbance. So here on the left side, I have just a little generator that's going to create what's called a pulse, just a single wave that's going to move through, and this is going to move through this, let's just call it a spring or a rope or something. But when we talk about moving through a medium, this thing right here would be the medium through which it moves. And a medium is just simply going to be the material that it's moving through. It could be a spring, could be a rope, could be water, could be air, could be empty space. Okay, so in order to create a wave, the first thing I need to do is create a disturbance. So I'm going to create a disturbance by just creating a little pulse there. Okay, I'm just going to decrease the damping and the tension a little bit here. We'll talk about those things. But I'm going to create just a simple pulse. And you notice that when I create that disturbance there on the left side, you'll see that all of a sudden now I have a wave that is moving through the medium. Okay, you'll see it travels here to the right. It's hitting that clamp and then it heads back to the left. It hits the generator and it goes back and forth. And the idea is that this wave was created by the disturbance. The disturbance was energy. Essentially, it's the thing that was moving up and down. That motion, think of that as kinetic energy, is now being transferred through the object. And this is how waves work. When we think of, for example, a sound wave, as you hear me talk, it is my voice created by the disturbance of my vocal cords. That disturbance affects the air, because that's the medium through which sound is traveling through, until it hits your ears, and then your brain perceives it as sound. So a wave, again, is going to be a movement of energy created by a disturbance that's going to move through a given medium. All right, so again, a wave is created by a disturbance. So there's two ways in which we can create a disturbance, and it's dependent upon the medium through which we have. So imagine up here I have a slinky, okay? The first type of wave we're going to look at is what's called a transverse wave. And a transverse wave is when we create a disturbance that is perpendicular to the direction of the medium. In this case, the spring is left to right, which means that when I create a disturbance, that disturbance is going to move from the left side of the spring through to the right side of the spring. So a transverse wave is when I'm going to create a disturbance perpendicular to the direction it's going to travel. So to show you what it looks like, it would look something like this. Notice the hand moving up creates a pulse. Does it again, creates a pulse, but notice that that pulse moves from the left to the right. Okay, so that's considered a transverse wave. When we create a transverse wave, there's two things that we get. We get what's called a crest. That is when we look at this position right here, and think of this position as the at-rest position. What's also called, fancy word is called equilibrium. So this is like the equilibrium or rest position of whatever the medium is. Okay, that when I create that disturbance upward, that's called a crest. If I were to continue that disturbance downward, that's called a trough. Think of trough as what piggies eat out of, okay? A complete wave is going to be an entire crest and an entire trough. So that would be a complete wave that we have there. And this is why I was kind of calling this a wave pulse, because when I showed the video, it was just the crest and not the trough. So that would actually be a half a wave, which would be just a wave pulse. So an entire wave is going to be a crest and a trough. And this is, again, what's called a transverse wave. The second way in which I can disturb this medium is instead of up and down perpendicular, that I'm going to disturb it parallel to the direction of motion. So again, think of the slinky as being a left to right medium. That means my disturbance is going to move in the same direction, left to right. So let's take a look at what that's going to do here. So again, notice the hand is going to disturb it back and forth. And you'll see that we get these points where we have the wave kind of tightly bound up and also spread out. Okay, so what we saw again is if I were to go back, whoopsie daisies, and just kind of show it again, you'll see the disturbance moving forward and back. And again, forward and back, and notice how the wave still moves forward. All right. So if I were to just pause it quickly there, I want you to notice that when we create a longitudinal wave, because we are disturbing it differently, what you're going to see is you're going to see, different than a transverse wave, you're going to see these areas where you have the coils of the spring very tightly bound and different areas where the spring is spread out. So think of this as like the crests and the troughs, but instead for a longitudinal wave, we call these compressions. So compressions would be all the points where the spring is tightly bound. And then rarefactions. Think of, I just like to say rare and then factions, rarefactions. But that is where the spring or whatever medium is going to be more spread out. And you'll notice here the coils are going to be a little bit more spread out. So it's kind of like the crest and the trough, but because we're moving forward, we get these points of compressions and rarefactions. Sometimes longitudinal waves are also called compression waves, if you've ever heard that term used before. So we have longitudinal and transverse waves are two types of waves we're going to look at. All right, in this first example, we're just going to look at our understanding of transverse waves, crests and troughs, and we're going to look at how many complete waves do we have. So understand that a complete wave is going to be a crest and a trough for a transverse wave, and a compression and rarefaction for a longitudinal wave. So it is a complete up and down motion. So again, these are transverse waves because we'll see the disturbances going up and down while the wave is moving forward in our medium. And again, this gray line is going to represent that rest position or equilibrium position if there was no wave moving through the medium. So if I want to know the number of waves, one simple way to do it is just to count the number of crests and troughs. So if, say, I have 1, 2, 3, 4, 5, 6 crests, and on the bottom I have a same number of troughs, 1, 2, 3, 4, 5, 6. So since I have an equal number of crests and troughs, that means for every crest and a trough, we have a complete wave. So if I have 6 crests and 6 troughs, that would be 6 complete waves that I have shown here in this diagram. Another way to do it is if you were to literally draw on this diagram, I have 1, I have 2, I have 3, 4, 5, and 6. Must be a complete crest and trough. Next diagram, I have, in this case, if I were to again count crests and troughs, I have here 3 crests and I have 2 troughs. So notice here that they are uneven. Okay, so if they are uneven, it gets a little bit more tricky to realize that for a wave, I need a crest and a trough. So I have here in like the first one, a crest and a trough, but then I have just a crest at the end. So anytime the number of crests and troughs are uneven, that means I do not have a whole number complete wave. So in this case, I know that I have 2 waves, but I only have a crest, so that means that I would have here 2.5 waves. So if the numbers are ever uneven, then you know you just have a number of waves that's going to be halfway or somewhere in between the the whole numbers for the crests and troughs that we have. All right, next thing we're going to look at are the basic properties of waves, and this counts for any wave, whether it's transverse or longitudinal. All right, so there's going to be some of these basic terms that we're going to look at as we talk about waves moving forward. So the first one, obviously a wave is created by some sort of disturbance. So that disturbance represents the amount of energy that I am putting into that medium to transfer from one point to the next. So if I create, let's say, a tiny disturbance versus a larger disturbance, that represents the amount of energy that I place in that wave. What we name that is what's called the amplitude. So the amplitude is our first term that represents the amount of energy that we're putting in. And the way we measure the amplitude is the distance that wave is from its tallest or lowest point to its resting position or equilibrium position. So for example, in this first diagram, my amplitude would be from the tallest point to that equilibrium position. That'd be A. I can even look at it from a trough. That'd be A. Now, essentially, the distance of my crest and the distance of my trough for any given single wave created by the same disturbance should always be the same. So as long as we have a wave from the same disturbance, we should hopefully get, okay, that amplitude to be the same. The only time it's going to change, and we're going to look at this, is anytime a wave interferes with another wave, and we'll talk about that. But again, the amplitude is going to be that height from either the tallest point or lowest point to that equilibrium position. And the size of that amplitude is going to represent the amount of energy we have in that wave. The way we measure that amplitude is, since we're looking at a height or a distance, it's always going to be measured in meters. So amplitude in meters represents the height or the amount of energy in a wave. All right, next one, this is going to be an important one, is what's called the wavelength. The wavelength is what it says. It's the length of a complete wave. So in a simple sense, you have from A going up and down, crest and a trough. That would be a complete wave. So the wavelength would be the length of the distance between the 2 points here, A to E. Okay, so we can think of the wavelength as the distance from A to E, whatever that distance would be considered the wavelength. Now, the technical definition is that a wavelength is going to be a distance from two identical points on a wave. So, for example, I chose A and C, but that's not the only way to find the wavelength. If I look at the wavelength from, let's say, B to F, those are identical points. That would also work. I could look at C to G. Okay. Now, why am I choosing C to G? Well, first of all, going back, I chose B to F because those are both crests. I could have chosen both troughs. I just don't have another trough. I'm choosing C and G, and you'll notice that the distance works out. But notice that's where the point where the wave is starting to go downward, starting to create a trough, and that's the same thing here. It's starting to go downward. So we're trying to find two identical points on consecutive waves, if you will. Okay? Now, we measure waves in meters. Again, it's a wavelength. And then you're going to see something new, our symbol for wavelength. Amplitude was easy because it was a capital A. But you're going to see this new letter. It's actually the Greek letter called lambda. Okay, so lambda. Lambda is going to be the symbol that we use for wavelength. And the reason why we're using that symbol is because the letter W is just used for other things. So we're going to use that symbol lambda. So when you see that, that is representing the wavelength. All right, so we're going to take a look first, next example, at determining the wavelength. So in these diagrams, again, you have those waves created within our medium. And here you're showing a bunch of crests and troughs, and then you're given the length of the medium, okay? So instead of a wave pulse like I showed you, think of this as like a continuous pulse, generator just continually going up and down. It's creating this wave within the medium, okay? And I know that the length of the string is going to be 4 meters. Now, just because I'm giving you the length is 4 meters does not mean that's the wavelength. The wavelength is the length of a complete wave. So if I look at this diagram, a complete wave is going to be a crest and a trough, okay? So notice I have a crest and a trough. So here within this length of string, within 4 meters, I have 1, 2, 3, and 4 complete waves. So within 4 meters, I have 4 waves, okay? So when I try to find the wavelength, what I want to do is figure out the length of one wave. So if there's 4 meters or 4 waves in 4 meters, that means the length of one wave should be 1 meter. Okay, the way to do this mathematically is, again, notice how do I get 1 out of 4 and 4 is I'm going to take the length and I'm going to divide it by the number of waves that I have. So essentially what I get is 1 meter per wave. So that would be the wavelength in this case, and there's our symbol. So if I look at this next one, this one's a little bit sassier, but I have here 1, 2.5. So I have 2.5 waves in this length of 4 meters. So if I want to find the wavelength, I'm going to take the distance of 4 meters, which again is still the same, and I'm going to divide it by the number of waves, which is 2.5 waves, and that will tell me then the wavelength, which would give me in this case 1.6 meters. Okay, so wavelength again is just going to be the length of one complete wave, which we can find if we know like information on the number of waves that we have within a given medium as well as the length of that medium. Okie dokie, artichokes. Last one here is we're going to have what's called the frequency. Now this one's sassy and it's going to be, as we're going to find out in our next section, it's going to be related to wavelength. So the frequency, when you think of that word frequency or frequency, how often it happens. So the frequency is going to be the number of waves that we have that pass through a given point within our medium in a given amount of time. So it's kind of going to be related to the speed of the wave. But what you'll see here is that here I have a high frequency. So notice that I would have, in terms of crests and troughs, so if I think crest plus trough versus here crest plus trough, in this medium I'm going to have a lot of waves. Okay, and here I'm not going to have as many waves. In this case, I'm going to have about 1 and almost 2. Here I'm going to have a lot more waves. So in this case, the frequency here is going to be a lot more than it would be here. Okay, so frequency is going to be the number of waves in a given amount of time. So frequency is going to be labeled with a lowercase f, kind of like a script F you'll see me write. All right, unit-wise, it's going to be the number of waves that pass through a given point in a given amount of time. So think of it as waves per second. This is going to be a new unit. I actually have a kind of typo there, but it's going to be a new unit, oh my God, called a Hertz. Okay, now I have it wrong up here. It should be a capital HZ. But HZ, which you might have seen before, is sometimes used in electronics, especially television. You might see a 60 hertz or 120 hertz. But that's going to represent the frequency in waves per second. Okay, so it's going to be a time-based thing, but it's the number of waves we're going to have in a given amount of time. That's called frequency. Okay, so in this next one, we're going to look at the frequency. Again, it's going to be very similar to how we looked at wavelength, but instead of looking at length, we're going to be looking at time. So you notice here that I have the same waves from before, and I'm given the time it takes for that wave to pass through that medium. So here it takes 0.5 seconds. So frequency is going to be, again, the number of waves in a given amount of time. So think of this as waves per unit of time. So I got to figure out the number of waves. So here it's a crest plus a trough. So 1, 2, 3, 4, 5, and 6. So I'm going to have 6 waves, and the time is going to be 0.5 seconds. So if I take 6 divided by 0.5, that means my frequency is going to be 12 hertz. 12 waves for every second. So if this is a half a second, if I were to double this for an entire second, I would have to double the number of waves to give me 12. So that would be my frequency. Okay, same thing here. Again, I have 1, 2.5 waves. So my frequency would be 2.5 waves in a time frame of 0.5 seconds. So if I take 2.5 and divide it by half a second, my frequency here would be 5 hertz. So notice that when I have more waves in a given amount of time, that I get a larger frequency. All right, so we introduced the concept of a wave created by a disturbance that moves through a medium, representing energy being transferred. We had the type of waves, the transverse and longitudinal. So now we got the different components like crests and troughs, compressions and rarefactions. And then lastly, our terms of amplitude, wavelength, and frequency. So as we progress through these different sections on waves, we'll be focusing on some of the relationships between these variables we talked about here. If you guys got any questions, make sure you jot them down. Let me know. Good luck on those concept builders. We'll see you next time.